Today, we're diving deep into the microscopic, gate-level mechanics of how digital systems actually capture a single moment in time. If you've ever wondered how your hardware manages to remember a precise piece of data right when it needs to, well, you're in exactly the right place. Let's get into it. Okay, here's our roadmap. First, we'll cover capturing the moment. Then we'll break down the positive edge configuration with 6 NANDs, move on to the negative edge with 6 NORs, and finally, do a quick NAND versus NOR comparison. Section 1. Capturing the moment. Before we get into the circuit diagrams, let's just ground ourselves in what we're actually looking at. At its core, we're talking about a flip-flop. Now, you know this is a sequential circuit element, right? It samples its data input, which we simply call D, and it changes its outputs only at very specific times, dictated by a clocking signal, or CLK. I always like to think of a flip-flop like a digital camera shutter. It honestly doesn't matter what's happening in front of the lens the rest of the time. It's only going to sample that data input exactly when the clock signal tells it to snap the picture. But how does that shutter know exactly when to snap? Well, it clicks based on the clock's transition, which we call an edge. A clock signal is essentially a square wave toggling back and forth between a low voltage and a high voltage state. Positive edge-triggered flip-flops change state on that low to high transition. And on the flip side, negative edge-triggered ones change state on the high to low transition. It's really all about catching the data on that precise momentary slope. Section 2. Positive edge with 6 NANDs. So how do we actually build this digital shutter using logic gates? Check out the sheer elegance of this positive edge-triggered design. We're looking at a 6 NAND gate configuration here. Over on the left, you've got your two inputs, the clock and the data input, D. Notice how they map directly into this cluster of 4 interconnected NAND gates. That's gates 1 through 4. These front gates act as your steering and control logic. Then right over on the right-hand side, gates 5 and 6 form that classic cross-coupled structure. That right there is your memory core, the latch that actually holds onto your Q and Q' outputs. All right, let's step through exactly how this operates gate by gate. Starting with step 1, the input stage. Imagine the clock signal is currently low, sitting at a 0. Because of how NAND gates work, where any 0 input absolutely guarantees a 1 at the output, gates 2 and 3 are forced to output a 1. Moving to step 2, the intermediate stage. This means those intermediate states, S' and R', are both just chilling at a 1. So in step 3, for our active low SR latch formed by gates 5 and 6, a 1 and 1 input means hold state. Nothing changes. The shutter is completely closed. But here's where the magic happens.
Let's say our data input D is high. Since S bar and R bar are both high, the output of gate 4 is 0, which in turn makes the output of gate 1, 1. Now, when the positive edge arrives, it forces the output of gate 2, or S bar, to 0. This is the set situation, and thus, output Q changes to 1. It is fed back to the upper input of gate 6, which forces Q bar to be 0.
Now what if data was 0 when the clock went high? Well, gate 4 would output a 1. Since S bar is also high, all 3 inputs of gate 3 are high, which allows gate 3 to drop down to 0. R bar is now 0 and S bar stays at 1. It's a reset situation. Hence, Q bar changes to 1, which is fed back to the lower input of gate 5. Since its upper input S bar is 1, Q becomes 0.
The split second that clock hits high, those front gates lock out any further changes from D. They literally capture that exact moment until the next clock cycle. Section 3. Negative edge with 6 NORs. Having traced the positive path with our NAND gates, let's jump over to the mirror universe and look at the negative edge-triggered design. Visually, this 6 NOR setup looks almost identical, right? But functionally, it totally flips the script. Because we're using NOR logic, this circuit acts strictly on the high to low clock transition. Remember, with NOR gates, any input of a 1 forces the output to a 0. So when the clock is just sitting high, gates 2 and 3 are immediately forced to output a 0. This means our intermediate nodes, labeled R and S here, are both 0. That tells the final NOR latch at gates 5 and 6 to just hold its current state. The overall flow is strikingly similar to the NAND, but let's walk through the exact gate-by-gate logic of that negative edge. In step 1, the clock is high, so intermediate states R and S are forced to 0. Now the clock drops to 0. Let's say our data input D is a 1. Gate 4 receives that 1 and outputs a 0.
Moving to step 2. With the output of gate 4 at 0, and node R being at 0, when the clock changes to 0, gate 3 outputs a 1. Putting node S to 1 means it's a set situation. Thus, Q bar changes to 0, which is fed back to the lower input of gate 5. Hence, both inputs of gate 5 are 0, thereby setting output Q to 1.
Conversely, if D was a 0 when the clock dropped back in step 1, gate 4 outputs a 1, which forces gate 3's output to 0, making S a 0 in step 2. The feedback loop then ensures gate 2 outputs a 1, making R a 1. An S of 0 and R of 1 in step 3 resets the latch, making output Q a 0. Just like the NAND setup, the moment the clock transitions to 0, gates 2 and 3 lock their states. The circuit goes completely blind to any further noise or fluctuations on the data line until the clock resets by going high and falling low again. Section 4, NAND versus NOR comparison. So what's the big takeaway when we put these two architectural configurations head-to-head? Well, comparing the NAND circuit on the left with the NOR circuit on the right, you can really see the incredible structural parallels. They both use a super efficient 6-gate layout. They both use gates 1 through 4 to sample the data and lock it down right on the clock edge. And they both use gates 5 and 6 as the actual memory latch. But notice the functional inversion at those intermediate nodes right in the middle of the circuits. In the NAND circuit on the left, we're relying on active low logic, which is exactly why they're labeled S' and R'. The latch changes state when one of those nodes drops to 0. In the NOR circuit on the right, we're using active high logic, with nodes simply labeled R and S. That latch changes state when a node jumps to a 1. Ultimately, it's just two different mathematical paths to achieve the exact same memory function, triggered on opposite slopes of the clock wave. As our source material beautifully sums it up, they capture a moment. Whether an engineer goes with a low to high NAND architecture or a high to low NOR architecture, both of these edge-triggered circuits are hitting that exact same foundational goal. They take all those chaotic, constantly fluctuating electrical signals of a data bus, and they completely freeze a single, decisive 0 or 1 at the exact microsecond the clock commands it.
Hope it helped. Thanks for watching, and see you next time.